We were in 3.2 looking at infinite sets. Does anybody have any questions before we pick up there? Okay, so just a little review because we've been gone for a bit. The opening question of this section is how much bigger is the set of rational numbers than the set of natural numbers? And that's actually the question that needs to be answered in the Dropbox. So make sure we get that answered before the end of today, okay? Well, we've been looking at sets and discussing what was a finite set and what was an infinite set. So that was a whole week ago. We've seen that a non-empty set is finite if there is a natural number n, such that there is a one-to-one pairing between the set and the set 1 through n. Okay, so we looked at finite sets. In other words, you can count how many elements are in there and you stop at a number n. Whereas a infinite set, a non-empty set that is not finite, is infinite. So we looked at the set of natural numbers 1, 2, 3, 4, ... through n. Well, I'm going to ask you to get in groups today and think about a question regarding n. And we'll work in the groups a couple times today, so we'll take time to make sure everybody's in a group. So the ... means that we go on forever, right? Okay, so we're looking at the set n. That's the natural numbers, and you can abbreviate it natural numbers with the n with a double bar. Before we look at the question of the day, how much bigger is the set of rational numbers than the set of natural numbers? Let's look at a smaller set. So we'll call that set A. So the set A goes on forever too, but it starts at 2. 2, 3, 4, ... Okay. So in your groups, I'd like you to consider which set, if either, is larger, n or A. Okay, so that's what I'd like you to think about and discuss and have a rationale for. So how do we usually get in sets? Do you 4 usually work together? Is that how it is?
Yep.
Yeah. Okay, so you 4 can work together. And then how about you 4 can work together? Okay. Wait, definitely. Can you come down to this end of the table and work with these 2, please? And then back row can work together? Okay. And how about if you turn around and look at you? So online students, you can ask somebody about this too and give some rationale.
The other one doesn't have one.
The top one's bigger? How come?
The stuff's here. Oh, yeah.
Oh, every day. Okay, so you're saying the bottom set is all inside of the top set. What is your first?
I heard from someone that the second is going somewhere. this weekend. Especially because that one is bigger. That started at 1, and then the second one started at 2. I was gonna do that for 1 more.
So it's like one more. The number one. Which one? Oh, so you still talked about it?
Think so. It's bigger by one,
It's bigger than one.
but I got you one.
Okay. What is this group deciding? That the top one's bigger? So what I'm hearing in the groups then is that the top one's bigger because it has all of set A in it, and additionally it has the number 1. How big is each of those? Infinite. Okay. So remember, let me make this small. Remember what I had you all raise your right hand and square. If you have 2 sets, like the set of fingers on each hand, 2 sets have the same size if and only if they can be put in a 1-to-1 correspondence. So these 2 finite sets of my fingers are the same size because I can match them up 1-to-1. So let's write that down as a reminder. So 1-to-1 correspondence was the same as a 1-to-1 pairing. 2 sets have the same size if and only if they can be put in a, I could say into a 1-to-1 pairing or 1-to-1 correspondence. So you're saying there is no way to put those in a 1-to-1 pairing. Okay, try again. Try again. See if you can find a 1-to-1 pairing. See if there's a way to line all of those up. One set with the other. In your groups. If your group can figure out a 1-to-1 pairing, raise your hand.
Does zero count?
Don't zero on that. Don't zero on either of them.
So maybe like 1, 2, and then 2, 3, and then 4.
Yeah.
Oh.
I guess it's just like you could put 1 with 2. And that just keeps going, so they're both involved, so it's like included in the same time.
Okay, so when we go back to the definition, then we see a way to pair them up. And a lot of times I'll do that vertically. So first we want to list the sets so that none are missed. And then we pair them up. And I don't know whose I heard first. I think it was this group's. Who did you pair? What did you pair up first?
I guess I just paired up 1 with 2, and 2 with 3, and 3 with 4, and so on and so forth. So technically they are the same size because they're both infinitely matching.
Yes, they are infinitely matching. Yes, so we pair the 1 with the 2 with the 3 with the 4. We use little arrows to show that. And then we ask ourselves, are any used twice? So using numbers twice would be like if we took the number 1 or the number 2 over here and had it go to 1 and to 2. And then started going on like that. That would be using 1 twice, and so you can't do that and have sets be the same size. So this is a big no, don't do that. So are any used twice? We don't take the 2 and assign it to the 1 and to the 2 in the other set. Don't do that. Are any used twice? Are any missed? So are any of the numbers in the one set missed or in the other set missed? Are any of the numbers from one set assigned to go to two different numbers? So when we go back to the definition, then we decide that, in fact, the two sets are the same size, which is weird. So N and A are the same size, and we say that in set theory using the word cardinality. So two sets are the same size or have the same cardinality, and cardinality then doesn't have some of the connotations that size has, just sticks with sets. Two sets have the same cardinality or are the same size if they can be put in a one-to-one correspondence. So we could replace the word size here with cardinality. So that's kind of weird, because you can see set A is inside of set N, and there is a 1 in set N that's not in set A, and yet you can put the two sets in a one-to-one correspondence, so in fact they are the same size. But it's kind of interesting and odd. Now you had a similar question in your homework that several people emailed me about. So here's an example that's similar to one of your homework. Are the set N, the natural numbers, which are 1, 2, 3, 4, 5, ... and the set B that I just made up. So sometimes, in fact, B is called 3N because it's the multiples of 3 times the natural numbers. So you could change your B into a 3N. 3, 6, 9, 12, 15, ... Are they the same size? So what we do with these infinite sets is we look and see, can we find a way to make a one-to-one pairing? And I like to do that by listing them vertically. Oops, I wrote 8 because I was copying from above, but no, we're looking at 3N here. So the ... after the 6 means that the natural numbers just keep going. And 3N I can list so that I'm not missing any. And none are listed twice. And I can go ahead and make a one-to-one pairing. How would I make a one-to-one pairing here? Yeah, just go right across from each other. So there is more than one way to make a pairing, but the most straightforward is to just go right across from each other. Okay, so the 1 goes with the 3, the 2 with the 6, the 3 with the 9, the 4 with the 12, the 5 with the 15, and the 6 with the 18. So what we're actually doing then, you could actually have a little formula. The number n goes with the number 3 times n. To me, those are the most satisfying kinds of pairing, because then you can say, oh yeah, like if n is 3, it goes with the number from 3n that's 3 times that, or 9. Or if n is 4, it goes with 12. So in your one problem where you have to answer a question like this, you'll have multiples of 8 or multiples of 4 or some kind of multiples. You're supposed to enter 3n or whatever your multiple is. And so some of you are trying to get that right and it wasn't working. It's because you're supposed to put 3 times n or 4 times n or whatever your particular problem is. Does anybody have any questions? let's make sure you understand this. Let me give you one with find a one-to-one pairing between the natural numbers and we'll call it 10n, the natural numbers that end in 0, except 0. Can you go ahead and illustrate that? This is a good example of a quiz question too, okay? So go ahead and illustrate that with little arrows matching up so that none are missed and nothing's used twice. And I'll come around and see how you're doing. If you're stuck at all, raise your hand, okay? That'd be hard for me. You're like, where's the arrow? So mostly what I'm seeing is the 1 goes with 10, 2 goes with 20, 3 goes with 30, 4 goes with 40, 5 goes with 50. So this is a one-to-one pairing. None are used twice, and none are missed. Each one is used. So we have these two sets are the same size, which again is really kind of weird because the one set is inside of the other set, and yet in fact the two sets are the same size. If you just looked at this, you might think, well, the one set's 10 times as large as the other, but no, the two sets are the same size. Here I'm going to put these all together. So we looked at 3 different sets that all turn out to be the same size. I guess four sets, because we have the natural numbers. We have the natural numbers less the number 1. Clearly a smaller set, but not smaller. In fact, the same size. And then multiples of 3 and multiples of 10. Those are all the same size. But that maybe seems pretty straightforward because, after all, those are multiples, or you can just shuffle. What if we try something a little different? Let's see if we can find a set that's larger than n. So far, these sets have turned out to be the same size, even though they look smaller. This is my day for breaking things. I don't think this is going to work anymore. Maybe it'll work on here. Oh, it froze. I think I just have to click here. So we were looking at sets that look to be smaller than n. Let's see if we can find some sets that are bigger than n. Does anybody have any suggestions of sets that seem like they could be bigger than n that we can work with? Try. What would we try? We'd try and put them in a one-to-one correspondence, right? So flip it. So what would those be? Then?
Make n like multiples of 10.
Can you, I'm not sure I understand. Can you tell me some of the numbers or that would be in it then?
Like 10, 20.
So it's not this set though, huh?
It is a set, but we'll flip it.
So we go dot 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 like that. Wait, no, I don't think I understand what you're trying to tell me. I'm not getting it, am I?
No, that's okay.
That's okay. All right. Okay, we'll keep going. Find some other ones that I can understand. Yes.
Can we make it that it's rational?
Rational numbers? Okay, so rational numbers. Oh, that's good. That will answer a question of the day, because that was what the question of the day is the rational numbers. How much bigger is the rational numbers than the natural numbers? So remember, those are the numbers that can be written as fractions. Do we have any other sets? Well, that's a good place to go, is to the numbers. You could look at your 3x5 card and look at some of the numbers on there. What sets of numbers did you have there on your 3x5 card? Yes?
Rational.
Irrational numbers? We're getting big infinite sets here. Remember how dense those were? Every two rational numbers had another rational number between them. That's sure not true about the natural numbers. And same thing with the irrational numbers. Every set of irrational numbers had another irrational number in between them. Yes?
But if they're all infinite, wouldn't they all be the same size?
That's what we're finding out. Is there another size of infinity? So that's exactly what we're trying to figure out. Is there another size of infinity, or is like infinity, when you say infinity, is that just it? Like that sums it up. Any other list of numbers from your cards?
Integers.
Integers. So of these lists, the one that looks smallest is the integers, because between every two integers there's not another integer, right? So the integers, remember, those were those went on forever in both directions. So the natural numbers are part of the integers. The natural numbers go on forever from 1 to the right, but the integers also have the number 0 and the numbers -1, -2, -3, and going on to the left forever, -4, -5, -6, and so on. So let's work in your groups. I'll say, is there a 1-to-1 pairing between the natural numbers and the integers? The integers are actually abbreviated with a Z with a double bar, which is kind of weird because Z is not a letter in the integers at all, but that's how it's written. So dot, 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 -3, -2, -1, 0, 1, 2, 3. So I'd like you as a group to, in your groups, see if you're able to come up with a 1-to-1 pairing. Or maybe work individually and then tell your group if you find one. Okay. So remember, -4, -5, -6, and so on. Those are all in there too. So if you get something in your group, tell the rest of your group.
Because we go that way. Because it goes to the, yeah, but this one is starts at 1.
So start by listing them. I see people starting to list them, and that's exactly what you should do. So you have to come up with a way to list Z without missing any, without any getting used twice. And you can reorder Z. You don't have to write it in the order it is.
So there's always like the negatives that always like 1, 2.
So keep coming, keep working on it. Because there's two things. Oh, very nicely done. Is that 10 years old? Somebody's got it. I don't think so. Was it? Oh, it's the wrong one. Okay. I didn't know what you looks like some got missed. Yeah. So we gotta shuffle them in. So listing them out.
They want to be,
Pass out first.
I see. This could be far more extensive So I'm lining them up.
Yeah, because you haven't lined them up yet, where some are missed, right? Some are not listed in your lineup, so you have to get a way to line them up where none are missed.
So the lineup based off people ready to start, it'll, as an example.
So there are these
Sometimes
crackers
people
that
that
go
use this.
Doritos.
Oh, so because there's 3 spots.
They're like
That's
the,
because that
you know, it's
starts
like the little cracker sandwiches, you can get like half.
So that doesn't, yeah, that sharing's not working. Because some are missed, you're right.
Yeah, but
So -4, -5.
Those are good cheesy crackers, cheese in the middle.
Yeah, they have two
So,
There's one that's a Doritos.
where's -4
4
on
and a
the
half.
list?
And then I didn't read the ingredients, so I had MSG.
I mean, on this one,
You're
you're
fine.
Could be the first
I
one.
just got corn.
No negative, no negative.
I had to keep in the piece with the room. And I was like, because I had two,
Speak,
had 2 of them.
whatever,
So I've
the
been
values don't
Collins
matter,
and
that's what
MSG.
Yeah, they do. That's what you have to do. You have to find a way to have the,
But I was like,
have them be ordered. That's exactly what you have to
because I
do.
always, my mom said, always get like a
So they
candy
have
and then
to-
something, like a banana or something.
Did your group come up with the way?
Yes.
Let's see.
Well,
Wait, where's, what goes with -4? Huh?
because
Oh,
it says
there's a dot
this,
right here.
so this goes
It's
further
infinite
that way.
ways.
It's harder to start with 1 because you don't know exactly where that, because it continues.
But you need to. So you can't, you have to have a number go right here with the 1. And if you put -3, -2, -1, 0, where, then you have 1 going with -3. But where's -4 going with?
0?
No, I got 0 going with, there is no 0 in the natural numbers. You gotta have every one of these numbers go with every one with one of these, with every one of these. So none are missed. Does your group figure it out? One group figured it out. Let's see. Where's my whiteout? So this is the natural thing to do because that's the way they're written up here. But when you do that, every element's not used. And none are used twice. Well, none would be used twice like this, but you'd miss the negative. You'd miss the -4, -5, -6. So what you have to do is find a way to write these out without missing any. You have to find a way to start counting them. Because that's what this does, doesn't it? It starts counting them. So I'll show you, and then you'll say, oh yeah, of course. Because once you see it, it's like a trick, and so much in math is. You put the 1 with the 0, because that's kind of the weird one out, right? And then put the 2 with the 1, and then the 3 with the -1. Then the 4 with the 2, and the 5 with the -2. And then the 6 with the 3, and the 7 with the -3. What comes next here? 4, and then what? So have we found, oops. Have we found a way to list them all without missing any? Have we found a way to list them all the integers without missing any? Yeah, because I don't know exactly where 100 is or -100, but I know they're down here on the list, and I could write out further and get to them. And I don't know where 1,000,000 and -1,000,000 are, but I know they're on the list, and if I write far enough, I'll get to it. So none of the positive or the negatives got missed in the integers. Zero's there, so this is the way I assign them. So this was a harder one because it's not, because you hadn't seen like the trick, if you want to call it that, to how do you count them all off? How do you list all of those integers without missing any? Does that help you to see how you can put them in a one-to-one correspondence then? Okay. So the answer here is yes. The natural numbers and the integers are the same size. They have the same cardinality. Now, when mathematicians first started discussing this, George Cantor brought it up first. And he was wildly contested, and mathematicians were very angry with him for saying things like this, until after some time they're like, oh yeah, he's right. Okay, so if this is confusing to you, you're not alone. The first mathematicians to hear this were like, well, wait, no, how can that be? Because this set is inside of here. So dealing with infinity presents these paradoxes that can twist your mind a little bit. But when you think about, and you remember what we go back to, two sets have the same size if and only if they can be put into a one-to-one pairing. And then you can see that, yes, we can put these into a one-to-one pairing. Well, that was our next smallest set. Let's move up. Let's move to the rational numbers next. So basically what we're seeing is if a set seems smaller, like 3n, or a set seems larger than the natural numbers, like the integers, if they can be put into a one-to-one pairing with the integers, they're still the same size. So you just have to find a way not to miss any and not to count any twice as you make your one-to-one pairing. So let's do that now with the rational numbers. So the question is, are the natural numbers and the rational numbers the rational numbers are abbreviated with a Q with a double bar, Q for quotient. So we're looking at, are the natural numbers and the rational numbers, those two sets, are they the same cardinality? Are they the same size? So we have to come up with a clever way to list the rational numbers, like we came up with a clever way to list the integers. Some way that you can put them in a list and not miss anything. So the very first thing is just how do you list all those fractions? So all the rational numbers can be written as fractions. And we start with the weird one, 0 in the middle. And then we're going to make a little chart from there. So what we'll do is make a column. And in the column we'll put all the fractions whose denominator, no, all the fractions whose numerator is 1. So we'll put 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, and then the dot, dot, dot means that that column keeps going up. So what would be next in the column where I put the dot, dot, dot? Yeah, 1 over 6. So that's what I'm trying to say with that. So 1 over 100 is way up there, 100 units higher up, okay? Okay, so now we'll put a column where the denominators, where the numerators are 2. So the top of the fraction is 2. 2 over 1, 2 over 2, 2 over 3, 2 over 4, 2 over 5, dot, dot, dot. So I have all the fractions whose numerator is 2. Then we'll do another column where all the fractions have a numerator of 3. 3 over 1, 3 over 2, 3 over 3, 3 over 4, 3 over 5, dot, dot, dot. Now, some of you can see there's problems already, right? Because we're talking about listing every rational number once. What's the problem here with that? Yeah.
Fractions like 1 over 1, 2 over 2, and 3 over 3 are all 1.
Yeah, these are all 1. 1 over 1, 2 over 2, or 3 over 3. Here's 2 over 4. That's the same as a half. So we're not listing all of these once. That's okay. We're making sure not to miss any right now. And when we come to a duplicate, we cross it off. Okay, so once it's time to order these, we will cross off anything that's a repeat. But for now, we're going to just make sure nothing gets missed. So we make another column with 4s in the numerator. Whoops, I missed 4 over 3. Now we could keep going with this, but hopefully you get the idea. So these rows keep going also. So the columns keep going up and the rows keep going to the right. So we're going to list every positive fraction in this grid. For example, if we have 50 over 7, 50 over 7 will go over to the 50th column and up to the 7th row. Or if we have 25 over 13, we'll go out to the 25th column and up to the 13th row. So every fraction that's positive is in this list, and there are even some duplicates. Now we'll do the same thing in the negative direction. So we'll have a column over here of negatives. So the first column has 1 in the numerator, that's a negative, and then negative 1 over 2, negative 1 over 3, negative 1 over 4, dot, dot, dot. Then a column with 2's in the numerator, negative 2 over 1, negative 2 over 2, negative 2 over 3, negative 2 over 4, dot, dot, dot. And then 3's in the numerator, negative 3 over 1, negative 3 over 2, negative 3 over 3, negative 3 over 4, dot, dot, dot. And 4s. So these rows also continue on forever, and these columns continue on forever as well. And in that way, we list every single possible fraction there is, and none are missed. Well, now it's time to count them off, right? I mean, we did this with the integers. We wrote out the integers, but they weren't first. They were first written out. Those integers were first written out in a way that didn't make it easy to line up with the natural numbers. So now we're going to find a way to line them up with find the way to line up the rational numbers without missing any. So what we do is we spiral. We start with 0, and then we go up to 1 over 1, and spiral down to negative 1 over 1, and then spiral over to 2 over 1. Then we come to 2 over 2, but that's a duplicate of 1. So we cross it off. Go over to 1 over 2, and then down to negative 2 over 2. That brings us to negative 2 over 2, but that's a duplicate, so we cross it off. And we keep going here. So we keep spiraling through, and as we come to duplicates, we cross them off. Oh, duplicate. 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 So as we continue through this spiral, we will hit every single one of the fractions in our grid, and we're going to cross off any duplicates. So we're going to hit only every single fraction one time as we cross off the duplicates. And that gives us a way then to make our correspondence. Here's our natural numbers: 1, 2, 3, 4, 5, 6, 7, 8. So here's our natural numbers, dot, dot, dot. And here's our integers, not integers, sorry, rational numbers, or Q for quotients. So we started with 0 going with the natural number 1, and then the fraction 1 over 1 goes, that's of course 1, goes with the natural number 2. And then the negative 1 over 1 goes with the natural number 3. That brings us to 2 over 1 to go with the natural number 4. We skipped 2 over 2, so that brings us to a half now to go with the natural number 5. And then after a half comes negative 2 over 1. That goes with 6. Then we're to the negative a half to go with 7. And over here to 3 to go with 8. So all of our, I'll put dot, dot, dot to show that that spiral keeps going. So all of our natural numbers are assigned to go with exactly one rational number, because we listed all the rational numbers that there were in these grids, and we crossed off the duplicates and then spiraled through. So every single element is in a one-to-one correspondence with the natural numbers to the rational numbers. None are used twice, and none are missed. So we're making a one-to-one pairing. Make each element in the first set go with exactly one element in the second set. So the answer to the question, are the natural numbers and the rational numbers the same cardinality? The answer is yes. So you should type that into the comment portion of the Dropbox. You can type in the natural numbers and rational numbers have the same cardinality. That's the answer to our first question. The natural numbers and the rational numbers have the same cardinality. That's probably faster for you to type in than to upload a picture, right? Or do you have? Can you enter a comment in without having to upload it? You have to upload a picture. Well, you might as well just do the picture then, or put it in a Word document, whatever is easiest. This is as far as we got in the first class, so this is where we'll stop here. And then on Wednesday, we'll look at some other interesting aspects that occur as we're looking at sets that are infinitely large. I'll see you on Wednesday. You can say the same size if you want instead of the same cardinality. Same thing.
Is it the same size set?
They're the same size. Yep.
Why don't you upload it? Is it the same size set?
No.
Just wondering.
3.2?